Hello. So now it is time for the third lecture, and in this time, we will be talking about the astronomical detector. So, astronomical detector detects the carrier of information, and for this detector, the lecture, we will be restricting our focus only to the photons, so electromagnetic radiation. Okay? So when we talk about the detecting photons, photons from the celestial object is detected through the detector and then producing signal. And this signal is usually recorded as electrons. And then later in this lecture, we will be learning why that actually we are the recording in terms of electrons. Okay. Then there are several characteristics of astronomical detector. First one is detecting mode and how that actually we detect exactly the photons. And we will be talking about the efficiency of a detector. Then we will be talking about the signal to noise ratio. So the first one is the how many the detected signal at the end. Said that the signal to noise ratio or detective quantum efficiency is talking about the noise characteristics of detector. Then the what wavelength regime that actually a particular detector is operating. So in terms of spectral coverage or spectral response. So such as CCD is only working in optical domain. Although there are actually some the far UV the wavelength regime, the CCD may actually also work fine. And some detectors, especially they designed in such a way that actually can be effectively used in infrared the wavelength range. So those are known as infrared arrays. And some special types of detector can be used in high energy domain, such as microchannel array. Okay? And the, the important the characteristics of the detector is linearity. Okay? So linearity is the one that actually that that providing the relationship between the detected signal versus incident signal. So having a linear the detector is important, and as you will see later. Then lastly, the sampling. And this sampling is actually saying what's the minimum size, the detectable structure for the given detector pixel size. But this is actually beyond the scope, so I decided not to really explain the sampling size. So there are three the hidden the slide at the end of the lecture note, and that is actually talking about this Nyquist sampling. In short, the minimum detectable size of the spatial scale is the twice the size of the pixel. That's what actually Nyquist sampling means. So when an instrument designer or builder are trying to develop some particular detector, then they need to actually think about, oh, what's the spatial scale of the object in the sky that actually that observers wants to detect. So small is the spatial scale. Then that instrument scientists need to develop design the detector in such a way that actually that detect the pixels has to be at least the half of that minimum the desired the spatial structure that actually that observers wants to observe. Then some response time, dynamic range, and physical size of the detector and the stability of detectors whatnot. These are all important characteristics, but we will not actually be talking about these in the lecture. So let's talk about the detection mode first. So how do you detect electromagnetic radiation or the photons. Okay, in terms of particle, it's a photons. In terms of wave, it's an electromagnetic wave. In infrared and the shorter wavelengths, so infrared, the optical visible light, and then UV, and then X-ray, and then gamma ray side, we are detecting photons one by one. So it is known as a photon detector. Okay? So how that actually individual photons are detected, as you will see in the next the video, we are converting the photons into the photoelectrons through the photoelectric effect. So one incoming photons will translate it into the one photoelectron. So by counting these electrons, we can count incoming incident photons. How do we count electrons? Just measure the current. Okay? So second type of detector is a thermal detector, oftentimes known as bolometer. Okay? So this is actually the measuring the difference of temperature when the photon is observed by the detector. So photon is an energy particle. So when the photon is observed or the detected by the detector, meaning that actually photon was observed, then the detector need to actually increase the temperature accordingly. So that change of the temperature of the detector because of the detected or observed photons. By measuring the temperature, we can actually deduce the influx or the strength, intensity of the incoming photons. So you are actually measuring the energy in proxy of the temperature. So these thermal detectors are widely used, ranging from infrared, radio, X-ray, and then gamma rays and whatnot. Okay? But we are not actually really spending time on this bolometer because that is a little bit beyond the scope of the astronomy 3010. So we will be mostly talking about this photon detector in this lecture. Thirdly, especially in radio wavelengths, when the wavelengths are actually really long, so that we can actually just have with our current technology, we can actually just isolate the single wave or a couple of waves in the incoming electromagnetic signal. So especially in radio wavelengths, okay, then where that actually we can isolate this wave, we can directly measure the phase and intensity and even the polarization of the electromagnetic wave. So this type of detector is known as wave detector. Okay? One important characteristics of the detector is how sensitive this detector is to the incident photons. For example, one good way of measuring the performance of the detector is if there is 100% incoming photons, what percent of the photons are detected? So if we can actually think about the ratio n, the number of photons detected divided by number of incoming photons. So if 100% of the incoming photons are detected, then quantum efficiency is 100%. That's the perfect the detector, right? And then the typical the photographic film has the QE of 0.5% to about 5%, and many of the semiconductors have the QE of ranging from 20 to 90%, and depends on the wavelengths and the materials or not. Even for the perfect the detector with the QE of 1, okay, so that means 100% of the incident photons are detected. Still, that actually the hypothetical perfect the detector has the intrinsic noise source. known as the Poissonian noise. Okay? So I will go to the next slide and then just come back. Okay, so Poisson noise. Okay? We all heard about the probability distribution function called Gaussian distribution. Gaussian distribution is the very typical, nice, the bell-shaped curve of probability. So this the bell shape, the curve or the Gaussian, the probability distribution is characterized by the two parameters. One is the average value, and another one is the spread of bell curve, known as sigma or standard deviation. So once we know the average and standard deviation, we can uniquely define that particular Gaussian function. So to uniquely define the Gaussian function, we need two parameters, average and standard deviation, or average and uncertainty. Okay. The contrary to this, the Gaussian distribution, Poisson the distribution, or sometimes Poissonian distribution, is handling and then governing the special counting experiment. So imagine that actually you have the counting division, such as the weather forecast could be predicted, oh, there's heavy rain, and in a unit area we should expect about 20 raindrops per second. So that 20 is the expected average value, right? Then the counting experiment is actually, okay, so with the expected average, the count of raindrop per second is 20. Let's just make the actual the counting. Even if that actually the rainstorm that actually produced the exactly 20 average 20 counts per second in any given second, because this is counting. Okay, so sometimes we will see 19, sometimes 21, and sometimes 18 or not. So there is a range of probability for the discrete number of the raindrops. So this is actually, there is an intrinsic, that the uncertainty for the any given the number of detected raindrops per second. So that raindrops per second is the event X. So X means P, the probability distribution, Poissonian probability distribution of 19. So that means actually 19 raindrops are actually recorded. Okay, given that actually that expected average the raindrops per second from that particular storm is 20, that is actually defined by this function. Okay, so look at this function. X is the event. Okay, mu is the expected average, the count, and that's the only parameter, right? So contrary to the Gaussian, which that actually we have two parameters, average and uncertainty, Poissonian distribution requires only a single the parameter, which is the average number. Then how do we actually calculate the uncertainty in Poissonian statistics? Strange and an interesting relationship for the Poissonian distribution is uncertainty of the Poissonian distribution is nothing but the square root of the average value. This is interesting. Because of this, oftentimes actually when we trying to measure the signal to noise ratio of some counting experiment, this signal to noise ratio, okay, or sometimes known as SNR, signal to noise ratio is basically the incoming signal divided by uncertainty, right? This, for the Poissonian distribution, that sigma becomes the square root of mu. So then this whole thing is mu over square root of mu, and signal to noise ratio is again square root of average value. So what this means, if you are expecting average 20 raindrops per second for the particular rain and the lightning storm, then uncertainty is nothing but the square root of 20. Okay? This is actually very interesting, the aspect of the Gaussian statistics. So remember that important the term the concept is the signal to noise ratio of Poissonian. The distribution is square root of average value. Okay? Then let's go back to the previous one. Even for the perfect detector with quantum efficiency of 1, this counting the error is still exists because this is an intrinsic counting noise, counting error. Okay, so imagine that actually there is imagine that there is the n photons were coming in. Okay, then its uncertainty is sigma, and this sigma is nothing but the square root of number of incoming photons. Okay, so signal to noise ratio, even for the perfect detector that actually detecting 100% of incoming the light, still that actually this detecting photon is the counting experiment. There is an intrinsic noise known as Poisson noise or counting noise or shot noise. Okay? So that is actually basically square root of the incoming the flux intensity. So imagine that actually you are the measuring 10,000 photons, then Poissonian noise is square root of 10,000, so that is 100. So if your detected signal is 10,000, then noise is 100, and then signal to noise ratio is 100. In other words, this is 1% measurement, even with the perfect the detector. Okay? So this quantum efficiency is a good I think the intuitively straightforward simple concept, but for the actual detector, that the quantum efficiency is not a really good indicator of the actual performance of the real detector. The real detector performance can be better described by this detective the quantum efficiency, so known as the DQE. Okay? The DQE is defined as the signal to noise ratio of the detection at the detector output. So signal to noise ratio to the square at the detector level versus signal to noise ratio to the square of the incident photons. So incident photons, this is actually purely the Poissonian, and this is the actual detector, the detected signal to noise ratio. Okay? So for the really perfect the detector, DQE and QE should be same, but the all realistic detectors, DQE is always less than QE. Let's look at the actual example of DQE calculation. Okay, so let's imagine that actually the hypothetical perfect the QE detector. So in this the experiment, we are actually using the theoretically perfect the QE equal 1. So 100% the quantum efficiency the detector. But this particular detector, although that actually is QE is 1, it produced the background noise. So this background noise, as we will see later on, this can be readout noise or dark current noise or straight from the sky background. So for without actually really specifying the source of this background noise, let's assume that actually this detector is somehow producing background noise level emission of 100 electron per second. Okay? And this observation, I think, detector was used to observe two different objects. One bright object, one faint object. So let's think about the bright object, the case. Okay, so because this is bright, 1 second observation, let's say that actually the 1 second observation with that detector observing this bright object actually produced the 10,000 electrons. Okay, so then we actually the signal to noise ratio of incident photons is 10,000 electron divided by square root of 10,000. So we have signal to noise ratio of incident light is 100. Now we want to actually calculate the signal to noise ratio out. Okay, signal to noise ratio of out is detected signal, which is 10,000, right? So 10,000 divided by noise. But now that actually in this the case, the perfect detector should have only the Poissonian noise, but now that actually we have background noise as well. So the total noise, okay, so sigma out total noise, the sigma out to the square. So the total noise can be the quadratic sum of each individual noise source. So the total noise to the square is each individual the noise source to the square. So this is actually what is known as the noise or errors added in quadrature. So first component is Poissonian noise. So how many the electrons that are subject to the Poissonian counting? There is the electron from the source. Okay, so that's the 100th, the 10,000 electrons. Then background over the duration of observation is 1 second. So background, the electrons actually produced, the number of background electrons produced during the observation is 100. So total number of electrons that are subject to the counting is not just 10,000, it's the 10,100. Okay, so this sigma Poisson to the square is 10,100, and background is produced the 100 count, so that actually the background noise to the square is 100. So sigma total of the uncertainty to the square is the 10,100 plus 100. So the output, the uncertainty sigma out is square root of 10,000 the 100 plus 100, right? So that's this portion is the signal to noise ratio of out. So signal to noise ratio at the detector divided by the perfect the signal to noise ratio of incoming, that's the 100. So that the DQE by definition is the signal to noise ratio at the detector divided by the signal to noise ratio of the incident flux to the square. So when we actually calculate all these, we will actually obtain 0.98 DQE for the bright object. Then let's just consider the faint object. This particular faint object was 100 times fainter. Okay, so this 100 times fainter object, to produce the same the resultant signal, the count of 100 the 10,000 electron, we need to observe 100 times longer. So 100-second observation produced 10,000 electron. Okay, then number of the electrons that are subject to the counting the experiment is Poissonian, right? So Poissonian, the counting the business actually need to count this the source electron plus during the 100-second the observation, that the number of the background electron produced was 100 per second during the 100 seconds. So it is the 100 times 100. So that's the the background electron produced during the 100-second observation is 10,000. So that means the background is 10,000 and source electron is 10,000. So number of electrons that are subject to the Poissonian counting is 20,000. So first term is the Poissonian noise. The second term is the background noise. That's the 10,000. So the total uncertainty to the square is 30,000. So take that actually that the signal to noise ratio out at the detector is detected signal is that the 10,000 electrons for the source divided by square root of 30,000. So when you calculate this signal to noise ratio at the detector is 57.7. So when you calculate DQE, so 57.7 divided by the incident, the signal to noise ratio, okay, that's the 100. So that means DQE is 33.3%. So using exactly the same detector, okay, we observed bright source, okay, and faint source. Faint source actually that the DQE was actually the measure that's 33%, while there actually the bright object DQE is 98%. So this DQE is actually dependent on the incident, the intensity of the incident light. So why it is actually this really good measure of the actual realistic detector? Because the detector is telling us that the detector's capability of detecting faint source. Okay? So DQE is the better the indicator for the detector's performance. Okay? Then lastly, let's talk about the linearity. The photon on the detector in astronomy is converting the incoming photons into the photoelectrons. So and then we measure the number of photoelectrons by measuring the electric current. Okay, so then by measuring the electric current at the detector, we can actually measure the number of incident photons. So really good, the detector should have the one-to-one linear relationship. So if the photons are twice stronger, then the final measured the electric current should be twice stronger, twice larger, right? If the incident light is 10 times the stronger, then final measured electric current should be 10 times larger. In such a case, is the perfectly linear. Then in that case, that actually this the linear the regime by measuring this the intensity or the slope of this relationship, we can always convert the recorded signal into the actual the incident the signal strength. So by the counting or retrieving the original number of incident photons from the particular source, that's our goal, right? So as long as the detector is perfectly linear, we can always retrieve the true incident number of photons. What about that actually that detector for somehow that actually at the near to the really the strong the incident signal. So this the incoming signal strength is actually expressed as time, because by measuring many different the intensity the source, I think simpler the measure is actually by observing the constant brightness object, but changing the observation length or duration. That way that actually we can calculate increasing the incoming signal strength. So this is why that actually that this the horizontal axis is actually expressed in terms of time. So imagine that actually that this is the time of observation for the constant brightness source. So that actually that x-axis is in fact is the incident, the signal strength, so number of photons throughout the observation, right? So imagine that actually for the really bright object domain, that detectors are actually getting saturated, so that actually that even if that actually additional or the incoming photons are actually coming in, detected signals actually stationary, stayed in the same way. So initially the nice linear relationship is actually getting saturation. Right? So this level is the saturation level. But before the saturation level, this detector, the response is actually starting to deviating from the linear relationship. So this is known as the non-linear domain of the detector. As long as actually that non-linearity is small, let's say that actually that less than 5%, this is actually still that repeating very consistently, so that actually this non-linearity can be still that actually the recovered. So recorded strengths can be still they're actually that they converted to the actual incident number of photons, as long as the actual non-linearity is not that actually large. But when you actually go into the larger and larger non-linearity, the domain, not only that actually detector is saturating, also that actually this detector behavior is not that consistent. So that actually there, even if that actually you measure the exact same the experiment and then repeat it, that recorded strengths oftentimes differ. Okay? And also that actually that the recorded number of electrons are subject to the Poisson counting noise as well. Okay? So this linearity is an important term, and this particular linearity, the curve, is the one actual the camera that actually the on board of the Hubble Space Telescope. So the when the Hubble Space Telescope Science the Institute they advise the actual observers, they actually they suggest that actually with this particular camera trying to stay below this the detected this signal strength. Okay, so if your source is too bright, then reduce the number of exposure time, something like that, or use some sort of gray filter that diluting the incoming the intensity of the light. So that is known as the neutral density the filter. So somehow that actually using the shorter wavelength, I think the exposure time, or using some filter decrease the incident the intensity of the light, so that actually your the final the recorded signal is stay below this the severe non-linearity regime. So linearity of the detector is the characteristic that actually we can use and then we can rely on to retrieve the original incident signal strength. Okay? So that's the introduction to the astronomical detector, and in the later the videos we will be actually talking about the specific designs of the particular the detector, such as CCD and infrared arrays and whatnot.